Every time you open Google Maps, your phone somehow knows exactly where you are. Whether you're walking through a crowded city, driving across a desert, or standing on a remote mountain, a tiny blue dot appears almost instantly. It feels effortless, but behind that simple dot lies one of the most sophisticated engineering systems ever built. And here's the surprising part. Not a single GPS satellite actually knows where you are. They never see you. They never track you. Instead, every satellite does something much simpler. It broadcasts an incredibly accurate timestamp and its own position in space. Somehow, your phone transforms nothing more than those tiny radio signals into a precise location on Earth. To understand how that's possible, we need to leave the ground and travel more than 20,000 kilometers above our planet, where the global positioning system begins its work. The GPS constellation consists of more than 30 active satellites orbiting approximately 20,200 kilometers above Earth. Unlike communication satellites that remain fixed over one location, GPS satellites constantly move across the sky, completing an orbit roughly every 12 hours. Their mission is surprisingly simple. They continuously broadcast radio signals in every direction, carrying only a few pieces of information with extraordinary precision. Each transmission contains the satellite's unique identity, its exact orbital position, and the precise moment the signal leaves the satellite. There are no photographs, no maps, and no information about your phone. Just numbers representing position and time. Those two pieces of information are enough to build one of the most accurate navigation systems ever created. Time is everything in GPS. Hidden inside every navigation satellite are multiple atomic clocks capable of measuring time with astonishing precision. These clocks are so accurate that they may drift by only a tiny fraction of a second over extremely long periods. Without them, GPS simply would not work. The reason is the speed of light. Radio signals travel through space at nearly 300,000 kilometers every second. If an atomic clock is wrong by only 1 microsecond, the calculated distance changes by almost 300 meters. A timing error so small that humans could never notice would make your navigation completely unreliable. Every GPS satellite continuously sends these precisely timed radio signals toward Earth, traveling at the speed of light. Each signal takes a little over 60 milliseconds to reach your phone. Although that journey is incredibly fast, it is still long enough for your phone to measure. That tiny travel time becomes the foundation for calculating distance with remarkable accuracy. Inside your smartphone, a dedicated GNSS antenna captures signals that are unbelievably weak after traveling thousands of kilometers through space. Before any calculations can begin, the receiver must amplify the signal without adding significant noise. A low noise amplifier boosts the incoming radio waves, while carefully designed filters remove unwanted interference from nearby wireless devices. The clean signal is then converted into digital data and passed to the GNSS baseband processor. Here, the receiver identifies which satellites are visible, synchronizes with their unique codes, and extracts the precise transmission time contained inside every signal. At this stage, your phone still has no idea where it is. It only knows which satellites it can hear and exactly when each signal arrived. The next step is surprisingly straightforward. Your phone compares the moment a signal was transmitted with the moment it was received. The difference between those two timestamps reveals how long the radio wave spent traveling through space. Multiply that travel time by the speed of light, and your phone instantly knows its distance from that satellite. One satellite can only tell your phone that it is somewhere on the surface of an imaginary sphere centered around that satellite. Every point on that sphere is exactly the same distance away. Obviously, that still leaves billions of possible locations. A single distance measurement is never enough to determine where you actually are. A second satellite adds another sphere. Where those two spheres intersect, the number of possible locations becomes dramatically smaller. A third satellite narrows the solution even further. Instead of an enormous surface surrounding Earth, your phone is now left with only a few possible positions that satisfy all three distance measurements at the same time. The fourth satellite completes the puzzle. Besides refining your location, it also corrects the tiny timing error inside your phone's own clock. Unlike satellites equipped with expensive atomic clocks, smartphones use ordinary crystal oscillators that are far less accurate. The fourth measurement allows the receiver to solve both your position and its own clock error simultaneously. This mathematical process is called trilateration. Contrary to popular belief, GPS does not measure angles or directions. It only measures distances. By finding the single point where multiple distance spheres intersect, your phone calculates its exact three-dimensional position with astonishing precision, often within just a few meters. In reality, however, GPS signals never travel through a perfect environment. As radio waves pass through Earth's atmosphere, they slow down slightly. Tiny variations inside the ionosphere and troposphere introduce additional delays that can shift the calculated position if they are not carefully compensated. Buildings create another challenge. In dense cities, GPS signals often bounce off glass towers, concrete walls, and metal structures before reaching your phone. Instead of following a straight path, the signal arrives slightly later after reflecting from nearby surfaces. Engineers call this multipath interference, and modern GNSS receivers use sophisticated algorithms to detect and reject many of these misleading signals. Satellite orbits are also constantly monitored. Even though every GPS satellite follows a carefully calculated trajectory, tiny gravitational forces from the Moon, the Sun, and Earth's slightly uneven gravity field gradually alter its path. Ground control stations continuously track every satellite and upload updated orbital information, ensuring that receivers always know the satellite's exact position. To improve accuracy even further, your phone combines measurements from many satellites at once. Modern smartphones rarely rely on only for satellites. In open environments, they may simultaneously track 10, 20, or even more signals, allowing the navigation engine to compare multiple solutions and significantly reduce positioning errors. Speed is equally important. If your phone had to download every piece of satellite information directly from space, obtaining the first position could take several minutes. That delay would make navigation frustrating every time you opened a map application. This is where assisted GPS or a GPS makes a dramatic difference. Using an internet or cellular connection, your phone downloads recent satellite orbital data, precise timing information, and visibility predictions before it even starts listening for GPS signals. With much of the preparation already complete, the receiver can lock onto satellites and calculate your location within just a few seconds. GPS is only one member of a much larger family known as Global Navigation Satellite Systems, or GNSS. Modern smartphones are designed to receive signals not only from the United States' GPS satellites, but also from Europe's Galileo, Russia's GLONASS, China's BeiDou, and several regional navigation systems. More satellites in the sky mean more measurements, better reliability, and greater accuracy. This multi-constellation approach is especially valuable in difficult environments. Between tall buildings, under dense tree cover, or near steep mountains, some satellites may be blocked from view. By listening to several independent satellite networks at the same time, your phone dramatically increases its chances of maintaining a stable and accurate position wherever you go. All of this processing happens inside a remarkably small GNSS chip. Hidden beneath its protective package are radio frequency amplifiers, precision filters, oscillators, analog to digital converters, dedicated digital signal processors, and specialized navigation engines. Together, these components transform extremely weak radio waves into meaningful positioning information. Every second, the receiver searches for satellite signals, synchronizes unique ranging codes, measures signal delays with extraordinary precision, compensates for atmospheric effects, corrects clock errors, rejects reflected signals, and continuously updates your location. Millions of mathematical operations are performed almost instantly, all inside a chip small enough to fit on your fingertip. The next time a tiny blue dot appears on your screen, remember what is happening behind the scenes. Dozens of satellites are broadcasting nothing more than accurate time and their own position in space. They never know where you are. Instead, your phone performs the calculations, solving one of the most remarkable engineering problems ever placed inside a consumer device. The engineering behind GPS becomes even more impressive when you realize that every satellite is moving at nearly 14,000 kilometers per hour while you are moving as well. Both the satellites and your phone are constantly changing position, yet the receiver recalculates the geometry several times every second to keep your location accurate as you walk, drive, or fly across the world. Engineers must also account for Einstein's theory of relativity, because GPS satellites travel at high speed and orbit far above Earth's surface. Time passes at a slightly different rate for their atomic clocks than it does for clocks on the ground. Without correcting these relativistic effects, navigation errors would grow by several kilometers every single day, making the entire system unusable. Before a GPS satellite is launched, its atomic clocks are carefully calibrated, and after reaching orbit, they continue to be monitored around the clock by control stations spread across the globe. These stations compare satellite timing, calculate tiny corrections, and regularly upload updated information, ensuring that every satellite remains synchronized with the rest of the constellation. Even with all of these corrections, your phone never stops verifying its own calculations. As new satellite signals arrive, older measurements are replaced, unreliable data is discarded, and the navigation engine continuously refines the solution. The blue dot on your screen is not a single calculation, but a constantly evolving estimate that updates many times every second. GPS has quietly become one of the most important technologies of the modern world. It guides aircraft across oceans, synchronizes financial networks, keeps communication systems aligned, supports emergency responders, and allows billions of smartphones to navigate with remarkable precision. Every time you check your location, you are witnessing decades of aerospace engineering, physics, and mathematics working together in perfect harmony. Yet despite its incredible capabilities, GPS is not magic. It is a carefully engineered system built on one simple principle: measuring time with extraordinary precision. Every improvement in clock stability, signal processing, and satellite synchronization directly improves the accuracy you experience on your phone. In the world of satellite navigation, time truly becomes distance. The next time your navigation app instantly finds your location, remember what happened in those few seconds. Radio signals traveled more than 20,000 kilometers from space. Atomic clocks measured billionths of a second. Specialized chips processed millions of calculations, and your phone solved an incredibly complex geometric puzzle, all before you even started moving. That tiny blue dot is far more than a marker on a map. It is the final result of satellites orbiting Earth, atomic clocks keeping nearly perfect time, engineers designing ultra-sensitive receivers, and advanced algorithms transforming invisible radio waves into precise coordinates. It is one of the clearest examples of how modern engineering quietly powers everyday life. From orbiting spacecraft to microscopic semiconductor circuits inside your smartphone, every part of the GPS system has one shared purpose: helping you know exactly where you are, anywhere on Earth. Millions of people rely on it every day without giving it a second thought. Yet behind every successful navigation lies one of humanity's greatest engineering achievements. The next time you see that familiar blue dot guiding your journey, you'll know it isn't the satellite finding you. It's your own phone, using nothing more than time, physics, and mathematics to calculate your position with extraordinary precision. That's the hidden engineering inside GPS. But GPS is only the beginning. Engineers are already developing next-generation navigation technologies that combine satellite positioning with inertial sensors, ultra-wideband radios, vision systems, and artificial intelligence. These technologies work together to provide accurate positioning even when satellite signals become weak or temporarily unavailable. Future navigation receivers will deliver centimeter-level accuracy to everyday devices, enabling autonomous vehicles, robotic systems, precision agriculture, and advanced industrial automation. What once required expensive surveying equipment is gradually becoming possible inside a smartphone that fits comfortably in your pocket. As satellite constellations continue to expand and receiver technology becomes more sophisticated, positioning will become even faster, more reliable, and more accurate. Future smartphones will not simply know which street you're on. They may identify which lane you're driving in, which floor of a building you're standing on, or even which doorway you're approaching. None of this would be possible without thousands of engineers working across multiple disciplines. Aerospace engineers design satellites that survive the harsh environment of space. Physicists develop atomic clocks capable of extraordinary precision. RF engineers create receivers sensitive enough to detect unimaginably weak signals, while software engineers transform raw measurements into meaningful locations. The next time your phone guides you to a destination, remember that the journey began long before the first map ever appeared on your screen. It began thousands of kilometers above Earth, where satellites continuously broadcast nothing more than accurate time. From those tiny timestamps, your phone reconstructs your position with astonishing precision, one of the greatest hidden engineering achievements of the modern world.